Hello students, this is Professor Chulai, and in this video we're going to begin Chapter 7 by looking at ionic bonding. As always, you can follow along with our new Chapter 7 workbook. By the end of this video, you should be able to explain the formation of cations and anions, and write the electron configurations of these ions, and also predict the charges on metals and nonmetals using our knowledge of electron configurations. Let's get started. So before we get into ionic compounds specifically, let's just look at types of bonds that we talked about earlier in the semester. We mentioned that metal and metals form metallic bonds, and the model is sort of this electron sea, where there's just electrons freely flowing in the setup. For metals and nonmetals, we have this idea of an ionic bond where electrons are transferred from the metal to the nonmetal, such that the metal will now have a positive charge, the nonmetal has a negative charge. And then for nonmetals and nonmetals, they form what we would call a covalent bonds because the electrons are equally shared between them. As we'll go through this chapter, we'll learn that it's a little bit more complicated than just these simple descriptions, and we'll see exactly why that is. And we'll start with the idea of an ionic bond. So what is an ionic bond? Well, we talked about how it is the attraction between a cation with a positive charge and an anion with a negative charge. So it's a bond between a cation and an anion held together by Coulombic attraction. What is Coulombic attraction? We learned earlier, let's create some space right here. We learned in our previous chapter about Coulomb forces between molecules, where the force between two particles can be written as the charge on one, let's write that as QA, Q is the charge, times the charge on the second, let's call that QB, divided by the distance R squared. So if the force is negative, it's an attractive force. If the force is positive, it's a repulsive force, meaning they push each other away. So if one of these is positive and the other one's negative, doesn't matter which one's which, then the overall force will be negative, and so it will attract. The two things will attract each other. This is why positive and negative charges attract each other, and this is what holds together covalent bonds. This is also why two negative ions don't form bonds, or two positive ions don't form bonds, because they have a repulsive force. They will push each other away. Okay, we'll come back to this a little bit more later in the semester as well. But then you might be asking, well, why do these elements form the charges that they do in the first place? Like, why do metals form positive ions, and why do nonmetals form negative ions? And the answer to that lies in electron configuration. And I'm going to reiterate a few rules that I think I barely mentioned in last chapter, but I'm going to mention them again. And that is, when we're dealing with electron configuration, let's say we're dealing with, let's look at the 2p setup. So this would be 1s, 2s, 2p orbitals, right? And let's pick an element. What should I pick? I don't know. Let's pick oxygen, because why not? We know oxygen will have 2 electrons there, 2 electrons there. Oxygen has 8 electrons total, so there's 4, 5, 6, 7, 8. Okay. In general, the rule is electrons like to either be in completely empty orbitals, completely filled orbitals, or completely half-filled orbitals, generally. This is why we don't see oxygen just hanging around as a single atom just floating around in the atmosphere, but rather oxygen exists as a O2 molecule, because oxygen by itself, when it's like this, is not very happy. It's not very stable, because this is neither completely empty, completely filled, or completely half-filled. It actually has some mix mash of electrons. What do I mean by completely empty? A completely empty 2p orbital will look just something like that. It's just empty. A completely half-filled 2p orbital would look like this. And if oxygen was like that, it would be happy. A completely, probably, it would probably be happy. And a completely filled 2p orbitals would look like this. Those are cases that electrons like to be in. Other cases, typically they don't like to be in. Of course, for every rule, there's going to be exceptions to that rule. So remember that. Electrons like to be in subshells that are either completely filled, completely empty, or completely half filled. Okay, so let's look at some electron configuration of cations, and we'll start with zinc. So let's write the electron configuration of zinc 2+, and to do that, we need to first look at the electron configuration of zinc without the charge, and then we'll remove 2 electrons to form zinc 2+ charge. As always, when you're doing electron configuration, it's good to have a periodic table handy. Right here, let's use, I don't know, a nice orange color. Right here, we have zinc. So if we're going to write this electron configuration, we know that we can start with argon. Argon's over here. That's the highest noble gas that's below zinc. So we can start with argon, and then we know we'll have some electrons in the 4s orbitals, and then some electrons in the 3d orbitals, right? That's how these columns are labeled. The n equals 1, 2, 3, 4 down here, except this first row here will be the 3d, the row below will be the 4d, and so on and so forth. Remember, this is the S block. The middle transition metals are the D block, and these guys over here are the P block. Okay, so let's write the electron configuration for zinc. We know that the 4s orbital should have 2 electrons in it, and then the 3d should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in it. Okay, let's do that. So for zinc 2+, we mentioned that we'll start with argon. Let's draw a little box for 4s, and then we need 5 boxes, 2, 3, 4 for 3d orbitals, because there's 5 orbitals in 3d subshell. We need 2 electrons in 4s, and then 10 in 3d. I'll half fill them first, and then fill them up. Okay. I also mentioned briefly that 4s and 3d are very close in energy, and typically when you're removing energy, removing electron, which is what we need to do, because this here is for zinc, but we need it for zinc 2+, which means we need to remove 2 electrons. We will oftentimes remove it from the 4s orbital first. Why? Because the 4s orbital, because it's a higher n value, the n value is 4, whereas here the n value is 3. Because of that, the common explanation is it's easier to remove those electrons because they're further away from the nucleus. So if we're going to remove 2 electrons to make this a zinc for make it for zinc 2+, 3d, we're going to remove these 2 electrons. And let's see if I can do that. Whoops, I removed the box. But that's what we will have for zinc 2+. So the electron configuration for zinc 2+ would be argon, because that's where we're starting with. 4s 0, right, because we don't have anything there, and then 3d still 10. We didn't remove any from the 3d subshell. So that's the electron configuration for zinc. Let's see the same for chromium. If you think you have a handle on this, you can keep going. The transition metals are always tricky, but you should be able to do these pretty straightforwardly. Okay, let's do chromium. Again, let's go over to our periodic table. Let's see where chromium is. So chromium is right here. So again, we'll start with argon, then we'll go to 4s, then 3d, and we'll need 2 in the 4s and 1, 2, 3, 4 in the 3d. So let's do that. We'll start with argon. We have 4s, and then 3d. We'll need 2 in the 4s, and then 1, 2, 3, 4 electrons in 3d. Now, remember I mentioned that electrons don't like to be in weirdly filled orbitals. They like to be either completely empty, completely filled, or completely half filled. And in this case, it's not really any of those. In fact, this one orbital here is empty, so this means that this 3d orbital is not happy. So what we could do for the case of chromium 3 plus is we could take one of the electrons from here. I erased my whole box, but that's okay. And we could put it over here. And that's what the chromium, this is for just chromium, not the chromium ion. That's what chromium does. So now this is completely half empty, which is okay. This is half empty, so that's okay. And nobody's unhappy. So this is probably what would happen. Now we need to take away 3 electrons to make it 3 plus. So as always, we're going to take away electrons from the 4s first because it's the outermost, the highest n value. So let's take that one away. And then we need to take away 2 more. So let's do 1, 2. I wish I didn't have to erase my entire box when I do that. But now this is what we end up with. So for chromium 3 plus, what we'll get is, we're starting with argon. 4s is now 0 because it's empty. And then 3d has 3 electrons in it. Right? So that's the electron configuration of chromium 3 plus. Alright, I mentioned that you could do potassium and magnesium by yourself, so pause the video now if you haven't done so and try those by yourself. Okay, let's look at potassium. Where's potassium on the periodic table? It is right here. Let's use a different color so you can see it. Potassium. So for potassium, we're going to start with argon again, and we only need the 4s subshell. And it'll have 1 electron in it. So argon, then 4s box, and it'll have 1 electron in it. Right? To form K plus, we need to remove that 1 electron. So this is the electron configuration of potassium. It's just argon, 4s 0, or you can even ignore the 4s 0, and it's just argon. This is typically what happens if you're not a transition metal and you're trying to form an ion. You will have the same electron configuration as a noble gas that's lower than the element that you're looking at. So for potassium or calcium, when you form an ion, you'll have the same electron configuration as argon. If you're sodium or magnesium, you'll have the same electron configuration as neon, and so on and so forth. This is why we tell you that everything in the first column, group 1A, form +1 ions, because they will lose an electron, and by doing so, they have the same electron configuration as the noble gas that's before it. Similarly, for group 2A, we told you that they form +2 ions. That's because when they lose 2 ions, they have the same electron configuration as the noble gas that comes before them. All right, let's show you how that's done again for magnesium. If you haven't done so, please do so now. So magnesium is right here, which means that we start with neon, and then we go to the 3s subshell. So we start with neon, and we draw a little box for 3s subshell. I can make that neater. And it'll have 2 electrons in it. So to form magnesium 2 plus, we remove those 2 electrons, and so the electron configuration of magnesium 2 plus is just the electron configuration of neon, the noble gas. So I hope that's making sense. That's how we can figure out what charges ions should have when they're not a transition metal. Transition metals are a little bit more interesting. Their ions are a little bit more complex. This is simplified. There's a few other things that come into play, but I'm just showing you some of the tricks that happen. For example, that we take away electrons from 4s first. So let's look at iron 2 plus. So iron 2 plus, iron is here, which means that we'll start with argon. We'll have the 4s subshell and then the 3d subshell, which will have 1, 2, 3, 4, 5, 6 electrons in it. So let's look at iron. So just for regular iron, we'll start with argon. We'll have the 4s subshell and then the 3d subshell. 4s will have 2, 3d will have 1, 2, 3, 4, 5, 6 electrons in it. Let's make sure that's correct. 1, 2, 3, 4, 5, 6. Okay. Now let's figure out what's the, oops. There we go. 1, 2, 3, 4, 5, 6. Yes, this is not completely half filled or completely filled, but we can't really rearrange the electrons to make it happy. right? Like we can't take one of this and one from 4s and put it into 3D and make it happy, or we can't take both and make it fill it into 3D and make it happy. So I'll have to stay where we are for now. Okay, now to make the 2 plus ion, we need to remove 2 electrons, and as I've mentioned, you remove from the 4s first. So we'll do that. Okay, so the electron configuration for iron is now argon, iron 2 plus, is now argon 4s0, 3d 1, 2, 3, 4, 5, 6. Now some of you might be thinking, well, this is still not happy. What if we just move this electron from away here? Whoop, too many things disappeared there when I did that. And put it over here. Now everything's half filled. Shouldn't we be happy? And yeah, that could happen, and probably does happen. But for most cases, the one that has actually the lowest amount of energy is this situation here, where they don't rearrange. And the reason for that might be complicated, which we don't need to get into now. Just form the ion first, and then remove from the 4s. Form the ion, but sorry, write the electron configuration for the element without the charge, so iron without the charge, and then just remove from the 4s first. And that'll help solve that problem to try to figure out what the configuration should look like. But for iron 3 plus, if you haven't done this, you probably should figure out that in addition to removing 2 electrons from the 4s, we'll also remove this additional electron from the 3d. So we'll end up with this situation. So we'll end up with argon 4s0, 3d 5. And that's the electron configuration for iron 3 plus. So to summarize, to write the electron configuration of ions, you just write the electron configuration of the atom with all of its electrons, and then for positive ions, you just remove the number of electrons that you need to make to have the charge that you require. For things like that are not transition metals, typically what you end up with are situations where you end up with an electron configuration that's the same as a noble gas. Okay, let's look at this anions, and you might imagine that it's the same process. So let's look at selenium 2 minus. Selenium is here in the periodic table. Let's use a better highlighter than that. Is here in the periodic table. So we'll start with argon, right? Then we'll have the 4s orbitals, then the 3d orbitals, then the 4p orbitals, right? That's how we label those. So let's draw the boxes. So we have argon, little box for 4s, box for 3d, and boxes for 4p, right? 3d has 5 orbitals, 4p has 3 orbitals. We know that 4s is filled and 3d is filled because it's in the 4p block. And then for 4p, it should have 1, 2, 3, 4 electrons in there. That's usually how I figure those out quickly. So let's put 4 electrons in there. 1, 2, 3. Fill them with single electrons first with the same spin, and then 4. Okay, so this is for regular selenium, but we need to add 2 extra electrons in there to make a -2 charge. So as you would suspect, we fill those with 2 more electrons. So 4p is filled. So this should be argon 4s2, 3d10, 4p6, right? Or this is the same as, what is that noble gas right there? Right? If you add 2 more electron, you get the same configuration as krypton, because krypton has the filled p orbitals. So this will be the same as krypton. And so you can imagine similarly for positive ions that are not transition metals, where you get noble gas that's just below, that comes just before the metal. For anions, when you add for their charges, you get an electron configuration that's the same as the noble gas that comes just after that element. So for selenium 2 minus, the electron configuration is the same as that for krypton. For I minus, then we could do this without even thinking about it. So I minus starts here. You can imagine then that it will have I for iodine starts here. For I minus, then you add 1 electron. You will get the same electron configuration as xenon. So you would expect that the answer for this is just xenon. But let's do it. If you haven't done it yet, do the whole process of drawing the boxes and filling them up first. And then I'll come back and show you how it's done. Okay, so for iodine, we'll start with krypton. Then we'll do the 5s, so this is n equals 5, 5s orbitals, then 4d, remember this is one lower, 4d, and then 5p. And 5p will have 1, 2, 3, 4, 5 electrons in it for iodine. So for regular iodine, let's do that. We start with krypton. We have our 5s set of block. 2, 3, 4. We have our 4D block, and then we have our 5P block. We'll fill these out. This has 2, this has 10. And we talked about how this has 5. But to get I minus, we add 1 extra one. It fills everything up, so we have the same electron configuration as xenon. Do the same for P3 minus and astatine 3 minus. And what you'll quickly realize is how we came up with those rules that we mentioned earlier in the semester about the kind of charges we have with anions. We talked about how, for example, elements in this column, the halogens, form -1 charge. Why is that? Because when they have one more electron, they will have the same configuration as a noble gas, and then their electron configuration, their orbital is completely filled. For this column right here, they form -2 charge because by adding 2 electrons, they completely fill their orbital, which makes them happy. And then here we get -3 charges because, again, same thing. They completely fill their orbitals, which makes them happy. All right, so this brings us to the end of talking about ions and why they form from an electron configuration point of view. I hope this all makes sense. Usually what we're going to do is just look at the periodic table to try to figure out the electron configuration of the element, and then either subtract electrons from that to form the positive cations, or add electrons to that to form the negative anions. All right, in our next video, we're going to talk about covalent bonding and how that's different, and I'll see you then. Bye.